For this question, the correct answer, or at least I'll say it this way. What I calculated was the acceleration is 3.72 meters per second squared. And the orbital period is 7.67 hours. Now, there's nothing new here. This is straight out of yesterday's example and straight out of your homework. So there's nothing particularly interesting here. But let's talk about how we get to the answer, because some of you are still having trouble. And you might want to write things down that help you, because clearly some of you need it. And some of you don't. And that's fine. You guys who don't, good job. So let's say Tara trips on Mars. Okay? So Tara trips on Mars. That means that Sarah's falling towards the surface of Mars. So there's an unbalanced force on Tara, mass of Tara, times A. That unbalanced force would be the force of gravity, but this acceleration would be the acceleration due to gravity on Mars. So we'll put a little GM there and an MT for Tara. It's flowing in the breeze. Thank you. It's got an atmosphere. So we'll do the whole thing in orange. The mass of Mars times the mass of Terra times G divided by separation distance here. Remember, this is the R that represents the separation distance squared. So we'll say that Terra is very close to the surface of Mars, so she's separated by 1 radius from the center of Mars. She's about to hit the surface, though. Not very hard, because the acceleration is not so bad there, so she has a long time to think about this. This side will be the mass of Terra times G. Oh, mass of Terra cancels. So anybody who falls on Mars will fall at the same acceleration. And that's it. That's how you find the acceleration of gravity on another planet. Not a whole lot to do there. So Terra manages to not trip so badly and recovers. So now Phobos, way out there, a distance of 6e to the 6th meters above the surface of the planet. Bless you, which means you need to use the radius of the planet in order to do this problem. What was the radius of Mars? There it is, 3.39 times 10 to the 6th meters. Now, this problem is different. We use the separation distance here as capital R, but some people have had confusion about what's the difference between the capital R and the lowercase r. Terra wasn't traveling in a circle. Terra was just falling straight to the planet. So we didn't have to worry about that. We just needed a separation distance. But Phobos is moving, right? It has a velocity because it's going around Mars. So because it has a velocity, there must be a centripetal acceleration acting on Phobos to make sure that it goes in a circular path around Mars. So it will not be this G that we're talking about. In fact, what it's going to be is net force equals MAC. Although there is an acceleration due to gravity on Phobos, and it's probably less than 3.7, that acceleration is being used to make Phobos change direction. So it travels in a circle. Therefore, I will replace the mass of Phobos, AC, with its velocity divided by lowercase r. Lowercase r is the radius of curvature. Here I still have mass of Mars, mass of Phobos, G over capital R. But we have to ask, at this moment, this is the right moment to ask, are these two distances the same? Is the radius of curvature and the separation distance the same for this problem? And this is not something that is going to be tricky on the test. The test will make it clear. So I'm not trying to make it tricky. I gave you the mass of Phobos, not because you needed it to solve the problem. You needed it to recognize how much smaller it is than the mass of the planet. Right? If we look, it's many orders of magnitude smaller than the planet's mass. That's there to tell you that the mass of Mars is much greater than the mass of Phobos. So that means these two r's are the same. I don't have to worry about the center of mass between the two. That's a high-level thought process, though. They're gonna tell you what you need to do there. They're not gonna make that secret. They will make it clear in the problem that you have to use the center of mass. And so would I if I was writing a test question. So in this case, we don't have to use the center of mass. We're gonna treat the center of mass as being at the center of Mars. And we just continue the problem now. The mass of Phobos cancels out. And now we don't want actually the velocity, we want the period. So we're gonna add something else here. The velocity is equal to 2 pi r over the period. Right? This isn't a complicated statement. Phobos is traveling in a circle and its speed is distance over time. We're just trying to work time in and not have velocity. So this is another substitution. You don't have to do it. You could do this in 2 steps. You could find the velocity first and then use that to figure out the period. But we're supposed to be at a higher level here. So we can do the algebra to get an expression for just the period. That's what we're doing. So I'll do another substitution after I cancel out one of the r's and get mass of Mars g over r equals, on this side, 2 pi r over t quantity squared. Now this just becomes algebra. Or if you want to plug the numbers in, plug them in, but I would just do the algebra first. So first, I'll square all of that stuff. Then cross multiply. None of this is interesting math, but you guys tend to have issues with algebra. So I'm writing out way more steps than I feel like writing out. And I'll solve it for t. What was that? T does not stand for tera. Believe it or not, T stands for period, because it's a capital T. And generally we use capital T for period. Something that happens over and over again. We use a capital T for the time it takes for it to repeat itself. Tera would never repeat herself. A little bit, because this is right. I mean, at the threshold, maximum level of difficulty. It's all the things we've talked about in a single question for an Atwood machine problem. Is it possible to ask this? Well, it's possible to ask. But why would I do this? Right? You have to get so many little details right leading up to this that this makes it really challenging, maybe too challenging. So how do you know, if I did this question, well, way less challenging, right? Just because we took one piece away, not a small piece, but by taking the angles away, I can focus you. This one's really about friction. This is really where you should focus yourself. How the friction interplays in this problem. Is this one out of the question? Well, maybe not out of the question, but maybe if I was doing this question, I want to focus you now on maybe how does the incline play with this a little bit, right? Because these two angles are complements of each other. Maybe there's an interesting interplay between those forces. That's a different kind of question. Do you understand what I'm trying to get at here is there's difficulty for difficulty's sake. But if I'm trying to figure out what you know, that's a different thing. So test writers are generally trying to figure out what you know, but there are some test writers whose whole goal is to show you how smart they are. Now, that's not great for you. This problem that we're going to do now, though, I think is within the wheelhouse, but it represents the threshold level, I think, for an orbit question, at least with what we've talked about so far. Imagine having a red dwarf and a black hole, which is funny because I make the black hole white. So, and the black hole is 4 times the mass. No, I want to go 3 times the mass. 3 times the mass of the red dwarf. Okay. So in this problem, I would want to know the period of the orbit of either the black hole or the red dwarf. Okay. Now, this may not be clear to you, but these two objects are relatively close to the same mass, which means they're going to orbit about their mutual center of mass, which is probably located somewhere around here. right? Closer to the heavier object than the far away object. And in that orbit, the black hole is going to have an orbit that looks something like this, right? That blue circle. While the red dwarf is going to have an orbit that looks something like that yellow circle. And the whole system is going to kind of be doing this. Right, that's how the orbit's going to look. Now, they're both going to have the same orbital period, but they have different orbital radii. This, I think, is a top-level question. It has all the stuff that we want to find. So we're going to start by asking a simple question. Which thing do you want to find the period for? We have to pick one. Do you want to find the period for the red dwarf or the period for the black hole? You know, you understand, it's the same for both, but we have to focus on one of them. One of them has to be the orbiting body. So, doesn't matter, you want to do the red dwarf, I heard somebody say it. Doesn't make any difference to me. So which one? Black hole's the thing we're going to look at? All right, so step one, we're going to have to figure out what the center of mass of the system is. We have to figure out where that location is. Because for the black hole, this represents the orbital radius, but this represents the separation distance. So to give us something to work from, we're going to say the distance between the two is d. And then we'll do everything based on that. Okay? Ready to begin the problem? Let's do the center of mass first. Since we're finding the orbital radius for the black hole, we'll make the black hole the 0 for reference, because we're trying to find the center of mass from the black hole. And if you recall, when we're finding center of mass, it's a summation. And we have to pick a reference point because it's going to give us a location. So we want the center of mass relative to the black hole. So we make black hole 0. Now, the top part of this is pretty straightforward. We take the mass of each object and multiply by how far away they are from the reference point. So the black hole has a mass of 3m, and it's located 0 distance away from the reference point because it is the reference point. Sorry to bore you. Then we add to it the mass of the red dwarf times its distance away from the black hole, because that's the reference point. Then we divide the whole thing by the total mass of the system, 3m plus m. This is going to give us r, the orbital radius. All right, so the top part's just going to be m, the bottom part's going to be 4m. I'm sorry, the top part's md, the bottom part is 4m, so this is just going to be 1/4 d. All right, that is the orbital radius. And our separation distance is d. So that's our step one. Usually, if a problem is going to require you to deal with the center of mass like this, they're going to have you find the center of mass first. That will probably be part A of any question that needs the center of mass. That's a big clue that you'll have to find the center of mass. But they usually will say in the problem details that the two things are orbiting about their mutual center of mass. That phrasing will usually clue you in that this is what you have to do. They're not going to hide it from you. Does that make sense? All right. Oops, don't want to do that. Let's just tuck this away and start the orbit part of the problem. Remember, the orbit part's going to have those three things again, the exact same problem you just did. So when I say those things, it's the exact same problem. Although I'm going to start it from scratch, it is the same problem. We did it just a second ago. So net force equals MAC. And this part you have to be careful. This mass is the thing that's doing the orbiting, and you told me it was the black hole. So we're doing this from the standpoint that that mass will be the mass of the black hole. So on the left side, I'll have 3m times m times g over the separation distance, which we know now to be d squared. The right side will be 3m times vt squared over r. I'm going to leave the r for a few minutes because we know we have another substitution to make after this, right? But I will notice right now I can cancel out the 3m's. So, just like before, the mass of the thing that's doing the orbiting cancels. So, mg over d squared here. But this side, I'm going to sub in for the velocity what we did before, 2 pi r over t squared times 1 over r. I just pulled the vt forwards and put in what I know for vt and squared it. I did that because I knew one of the r's was going to cancel eventually. So, I'm trying to make sure we see that before we start subbing in other stuff. But do you see that one of the r's is going to cancel? So, mg over d squared equals 4 pi squared r over t squared. There, I've canceled one of the r's. So don't come at me later saying, well, where'd that r go? But we know that r is equal to 1/4 d. So we're going to substitute in 1/4 d now. Right? This is the orbital radius. And I'm doing a lot of steps, and I'm just talking slowly to give people time to write things down that they need to write down. So when they ask, why'd you do that? You can write it down right now. That's why I did all those things. Now, happenstance that it happens to be a 4 and that we happen to have a 1/4. It's just a lucky coincidence, but those will cancel out, won't they? 4 times 1/4. And we're solving this for t. So I'm going to cross multiply. That was impressive. Hey, look, I'm always about moving stuff around. If you're going to sneeze, go ahead and do it. Your body's saying something to you. We're just solving for t, right? So one last step here and we're done. There it is in a nutshell. So what are we talking about here? We're talking about top level, I guess, difficulty. If you want to know, if you think it is top level, they have asked this question, I don't know, 2 or 3 times in 40 years. For a translunar injection orbit, that's a lot of fancy words. Throw those away. A spacecraft has to fly through a point between the Earth and Moon where the net force is momentarily 0. So imagine. We won't have time to do this question, but we can set it up. So, Earth, Moon. Can you imagine that there's a point in the middle where an object is experiencing 2 forces, one from the Earth and one from the Moon? So, there's a force this way from the Earth. That'll be mass of Earth, mass of spaceship, g, over, well, this distance to the Earth, squared. Good so far? And on this side, there'll be a force this way, mass of Earth, mass of Moon, mass of spaceship, g, and r to the Moon squared. That good so far? Well, there is, we'll say the Earth-Moon distance would have to be equal to RE plus RM. Does that make sense too? Remember, we are looking for RE or RM. That's what the question asks. Where is this? So you just set these two equal to each other. And then sub in something there so that you get it in terms of either RE or RM. Does that make sense?